Last class we discussed diagonal chaseable of a matrix. So today we discuss something when we say a linear transformation said to be diagnosable. Okay, so same thing before that, when we say two matrices are orthogonally, otherwise we say a matrix said to be orthogonally diagnosable. So there is a difference between diagnosable and then not that much different, but we get a invertible matrix, then we say is a just diagnosable. Orthogonal diagnosis means we will get a orthogonal matrix. Okay, so better write the definition now. So definition two real matrices are said to be orthogonally similar. So two real matrix, suppose we have two matrices A and B, two real matrices A and B are orthogonally similar. Orthogonally similar matrix. Similar if there exists a orthogonal matrix P. So there exists an orthogonal matrix. Orthogonal matrix we call P, such that one is we can write either B or A. We can write B equal to P inverse AP. So, but previously we discussed when we say two matrices are similar, if there is a invertible matrix P such that B or A equal to P inverse AP, and in this case we said just A is similar to B. But when you say A is orthogonally similar, then such a invertible matrix should be orthogonal matrix. So orthogonal means what? A into A transpose equal to here we P. So P into P transpose equal to identity, then we say it's an orthogonal matrix. Okay. So if the invertible matrix is orthogonal, that is P into P transpose equal to identity, then in that case we say A is orthogonally similar to B. Okay. So similarly, now what is when we say a matrix is said to be orthogonally diagnosable. So these are just we say two matrices are orthogonally similar. So similarly we can define what is when we say a matrix is orthogonally diagnosable. So diagnosable means what? There is an inverted matrix P such that P inverse AP is diagonal matrix, but here we get an orthogonal matrix. Is here we can write a matrix is orthogonally diagnosable. Orthogonally diagnosable. Orthogonally diagnosable if it is similar to orthogonally similar to diagonal matrix. It is orthogonally similar. Orthogonally similar to a diagonal matrix. Similar to a diagonal matrix. That is, so when we say A is diagnosable, yesterday we studied what is A. When we say A is diagnosable, if and only if there exists a invertible matrix P such that P inverse AP is diagonal matrix, where D is a diagonal matrix, the diagonal entries are eigenvalues of A. Now we say A is orthogonally diagnosable if this P should be orthogonal matrix. Orthogonal matrices are invertible matrices. So extra properties, the R should be orthogonal matrix such that P inverse AP is diagonal, then we say A is orthogonal matrix. The P should be orthogonal matrix. Or we simply say this A and D, that means what? A is orthogonally similar to a diagonal matrix. Okay. If A is orthogonally similar to a diagonal matrix, then we say A is orthogonally diagnosable. Okay. Similarly, this is for real case. That means a matrix, the entries are real case, then we use the term orthogonal. Suppose the entries of the matrix are complex number, then we use unitary matrix. Okay, so that is next definition. Two matrices are unitarily similar. So unitary similar means what? There is a unitary matrix P such that P inverse AP is P. Okay, that is next definition. Two complex matrix. Two complex matrices A and B. Two complex matrices A and B are unitarily unitarily similar. So when we say two matrices are unitarily similar, if there exists a unitary matrix, there exists an unitary matrix U, unitary matrix. What do you mean by unitary matrix? That is U into U star. So U star is nothing but you have to take the conjugate and then take the transpose. Okay. So U into U star into U should be identity matrix. So such a matrix, so unity matrix U such that B equal to U inverse A U. Okay. If B equal to U inverse A U for some unitary matrix U, then we say A and B are unitarily similar. So when we say a matrix is said to be unitarily diagnosable if A is unitarily similar to a diagonal matrix, same thing. So maybe we can write a matrix. So a matrix is unitarily diagnosable. Unitarily diagnosable. Unitary diagnosable if it is similar to, not only similar, is unitarily similar. So it is unitarily similar to a diagonal matrix. Similar to a diagonal matrix. Okay. Now we have an important theorem. Important lemma. This is very useful. So these two theorem definitions are very important. So when we say two matrices are orthogonally similar, then we can get an orthogonal matrix P such that P equal to P inverse AP. Then we say A and B are orthogonally similar. So when we say a matrix is orthogonally diagnosable, then the matrix is orthogonally similar to a diagonal matrix. So diagnosable means what? It's similar to a diagonal matrix. Orthogonally similar means what? Orthogonally similar to a diagonal matrix. So similarly here for complex case, a matrix said to be unitarily diagnosable if it is similar to not only similar, is unitarily similar to a diagonal matrix. Now the lemma, Gauss lemma, it says lemma name is called Gauss lemma. What the lemma says, there are two lemmas. First one, if you take any n by n matrix, real matrix, if an n by n matrix and n by n, not only real matrix, should be a real matrix. So if you take any n by n real matrix A has only real eigenvalue, has only real eigenvalues, then the matrix A is orthogonally similar, then A is orthogonally similar to an upper triangular matrix. It is similar to diagonal matrix that it become a diagnosable. but not all the matrices are diagnosable. But this theorem says if you take any n by n matrix, real matrix, suppose the A have only the real eigenvalues, then A is orthogonally similar to an upper triangular matrix. So similar to upper triangular matrix means what? There is an upper triangular matrix and should be invertible such that okay, there is an orthogonal matrix. So what is the meaning of this? There exists an P. The P should be orthogonal matrix, orthogonal such that P inverse AP should be upper triangular matrix. That is, below the diagonals are 0, above the elements at least one entries are at least non-zero. So any matrix is orthogonally similar to upper triangular matrix provided A as a real eigenvalue and then real matrix. So similarly, we can have a, suppose we have a complex matrix, then in that case that any complex matrix is unitarily similar to upper triangular matrix. Okay, that is the second one. Second part of the theorem, lemma. If you take any n by n, if you take every n by n complex matrix means what? Entries from complex number. So complex matrix is similar to, not only similar, it should be unitarily similar. Complex means unitary, real means orthogonal. So unitarily similar to a upper triangular matrix. Similar to an upper triangular matrix. Upper triangular matrix. It's always upper. But if this similar to diagonal matrix, then become a diagnosable. But in general, not all the matrices are diagnosable. Okay. But any matrix is similar to upper triangular. If A is either Hermitian matrix, if A is either Hermitian matrix. So Hermitian means what? A equal to A star. A star means what? So what do you mean by A star? A star is that first you take the complex conjugate and then take the transpose. That is A star. So Hermitian matrix. So Hermitian means what? So Hermitian means what? A equal to A star. A matrix satisfies the condition A equal to A star, then we say Hermitian matrix. Suppose A is either Hermitian or a skew Hermitian. So skew Hermitian means what? A equal to minus A star. So skew Hermitian means what? A equal to minus A star, then we say skew Hermitian. Either A is Hermitian or skew Hermitian or unitary or a unitary matrix, then that matrix is diagnosable. So all the Hermitian matrix is diagnosable, all the skew Hermitian matrix is diagnosable, all unitary matrix is diagnosable. Not only is diagnosable, is unitarily diagnosable. Okay. So then we get a unitary matrix such that we get a similar to diagonal matrix. So there are three matrices. If you take any matrix, either Hermitian or skew Hermitian or a unitary matrix, then it is unitarily diagnosable. Very important. So with the examination, they will ask, they will give some matrix. Maybe the matrix may be Hermitian matrix or Q Hermitian matrix or unitary matrix. So they will ask it is unitary diagnosable or orthogonally diagnosable, or just they may ask some other thing. So using this theorem, if it is Hermitian, then it is unitarily diagnosable. Okay. So look at this. Everything is a complex entry, right? Hermitian means what? The matrix entries are complex. Skew Hermitian again, the matrix are complex entries. Unitary also, the matrix are complex entries. For in the complex series, we use the unitary rule. Okay, so this should be unitarily diagnosable. So similarly, for the real case, symmetric matrix and then orthogonal matrix are orthogonally diagnosable. Okay, we will now we write in the real case. So for complex case, Hermitian, skew Hermitian, unitary matrix all are unitarily diagnosable. Now for the real case, what is the real matrix? The special matrix is symmetric matrix. Therefore, we can say as state as a theorem, the followings are equivalent. Any two matrix are equal. That is, for any matrix, for any n by n matrix, n by n real matrix, n by n real matrix, the following are equivalent. That is, one implies two, one implies other. So the following statement or following are equivalent. So what is the first statement? A is symmetric. If A is symmetric matrix, then it is symmetric. Then A definitely should be orthogonally diagnosable. So A is orthogonally diagnosable. That is, every symmetric matrix is diagnosable. Especially we can say it's orthogonally diagnosable. It's a very important thing. And then the columns or rows are orthogonally orthogonal vectors. Not only this, this A has a full set of, if it is n by n matrix, therefore there are n vectors, right? You can see, look at the column vectors or row vectors. So A has a full set of n orthonormal eigenvectors. Orthonormal eigenvectors. Because every matrix have an eigenvalue, so for each eigenvalue we have a corresponding eigenvector. That eigenvector form a orthonormal. So what do you mean by orthonormal? So eigenvectors. So suppose we say u and v, there are two vectors. We say this u and v are orthogonal or orthonormal. So when we say these two vector u and v is orthogonal, if the first condition is the inner product of u and v should be 0, and then the inner product of u comma u and the inner product of v comma v should be 1. That is, norm is 1. If you take the inner product of other different two vectors should be 0. Such a vector is called orthonormal. So instead of taking 2, suppose you have a n vectors. Suppose you can take u1, u2, etc. un, u1, u2, etc. un. We say the set of n vectors are said to be orthonormal if the first condition is, if we take inner product of uy comma different vector uj should be 0. Okay, for I not equal to j. If you take different vectors, the inner product is 0. If you take the same vector, the inner product is 1. If we take the same vector, that is uy comma ui, should be 1. The set of vectors satisfy these two conditions, then we say the set of vectors is orthonormal. So orthogonal means what? So orthogonal means what? Only the first condition satisfied. If a set satisfies only the first condition, then we say it's orthogonal. If it is the second condition, then we say orthonormal. Okay. So only the first condition, the inner product of any two different vectors are 0, then we say orthogonal. So we can write here. So suppose we have set of vectors v1, v2, etc. some vk is said to be orthogonal. When we say it's orthogonal, if only thing, if you take any two different vectors vi and then vj, the inner product should be 0 for I not equal to j. For different vectors, the inner product is 0, and we say orthogonal. For example, in R2, if we take the special example, so can anyone tell me that what is the orthogonal set? So in R2, suppose I am taking 1 comma 1 and then suppose I am taking 2 comma minus 2. These two are orthogonal because this is u vector, this is v vector. What is the inner product of u comma v is nothing but just you have to multiply term by term and then you have to sum. So 1 into 2, that is 2, plus 1 into minus 2 is minus 2. Therefore, sum is 0. Therefore, inner product of these two vectors is 0. Okay. Therefore, is orthogonal. But it is not orthonormal. Why? Because if you take the same vector u comma u, it's nothing but just 1 comma 1 dot 1 comma 1. Means you have to multiply term by term and then sum, we get 2. But this is not equal to 1. Therefore, this vector, this set of vectors is orthogonal but not orthonormal. Therefore, every orthonormal is orthogonal, but orthogonal vector need not be orthonormal set. Okay. So in R2, this set is a orthogonal but orthonormal, but not orthonormal. If you take this vector 0, 1 and 1, 0, 1, 1, 0. Suppose if you take these two vector, now this is orthonormal. Because suppose you take this is u and this is v. So what is the inner product of u comma v is term by term multiplication, coordinates multiplication, and then sum 0 into 1 0 plus 0 into 1 0, therefore 0. So what if you take the same vector u comma u, so it's nothing but 1 comma 0 dot 1 comma 0. So what is the coordinates multiplication? 1 into 1 1 plus 0 into 0 0, therefore we get 1. Similarly, if you take the v vector, so inner product of v comma v is what is that? 0 comma 1 dot is actually inner product dot, not usual multiplication. So 0 into 0 0 plus 1 into 1 is 1, therefore 1. Therefore, this vector is orthonormal vector. So we can give there are infinitely many orthonormal vectors in R2. So this is a one of them. Either you take 1 0 0 1. Can you give any other? The inner product should be 0 and the norm should be 1. If suppose we can convert, look at this first, if you take the first example, it satisfies the orthogonal condition, but it is not orthonormal. Therefore, we have to normalize this vector. It becomes a orthonormal vector. So how to normalize? So this is nothing but we define the notion norm of a vector, norm u. Okay, so norm u is nothing but, so by the definition we can say inner product of u comma u square root. Square root of inner product of u comma v, u comma u, they defined norm u. Okay, now suppose we have a vector v, but it is now the so norm 1 means what? Suppose norm equal to 1, then inner product of u comma u is 1. Because you take the square root both side, we get inner product of u comma u is 1. Okay. So if you take a non-zero vector, v is a non-zero vector, but this inner product of v comma v is not equal to 1. If it is equal to 1, okay, it's normal vector. But suppose the inner product of u comma u is not equal to 1, now we can convert or we can define new vector. So we call v1, we define v by norm v. Now if we take the inner product of v1 comma v1, it should be 1. The new vector v1 should be orthonormal, but the old vector v is not a normal. So in the case if you take what is the case I am taking? So if you take 1 comma 1, if you take v equal to this, then what is the inner product of v comma v is term by term multiplication, and then sum we get 2. But this is not normal because we get 2 not equal to 1. Now we have to define new vector v1 is nothing but v by norm of v. So norm of v is nothing but square root of v, inner product of v comma v, we define norm of v. So already we found that this is 2. If we take the square root, we get therefore 1 comma 1 by square root of 2. So square root of 2 means we are multiplying 1 by square root 2 each term. Therefore, what is the vector? We get 1 by root 2 comma 1 by root 2. Now we can easily check that this new vector v1 is orthonormal. Why? So what is the inner product of v1 comma v1? So inner product of v1 comma v1, sorry v1. So inner product of v1 comma v1 should be, what is that, dot product of the same vector, 1 by root 2 comma 1 by root 2 dot 1 by root 2 comma 1 by root 2. So multiply the term by term, 1 by root 2 into 1 by root 2, 1 by 2 plus 1 by root 2 into 1 by 2, 1 by root 2, 1 by 2. Therefore 1 plus 1 by 2 plus 1 by 2 is 1. Now we get a norm is 1. Therefore given any vector, it is not normal, then we can convert into normal vector by normalize. So normalize means what? So usually we say a given vector normalize means what? We have to divide the norm of the vector. So we say this is actually we define norm of the vector v, norm of v. So if you divide the norm of v to the given vector, that is a normalize. Okay, that is the process is called a normalized process. Okay, therefore the same problem. So this is not normal. The first problem, this is not orthonormal, but it's orthogonal, but it is not orthonormal. But we have to convert this into orthonormal set. What is that? So just okay. Sorry, please wait. Okay. Now anyway, so I lost some pages. Okay, now look at this. We know that this is the first example. This is not orthonormal, but it is orthogonal. Now we have to normalize each vector to get a new vector. So what I am going to do, I am going to divide norm of this vector. So what is the norm of this vector? 1 by root 2 is the norm. Okay, because square root of this. Therefore, we have to divide this number. Therefore, 1 by root 2 comma 1 by root 2. Okay, now what about this vector? So what is the norm of this? Maybe I call this vector is v. What is the norm of v? Norm of v is nothing but square root of inner product of v comma v, square root. Already we found that what is the, where is the, okay, what is the inner product of v comma v is nothing but 2 comma minus 2 dot 2 comma minus 2. So just multiply 2 into 2, 4, and then what is that here? 2 into 2 minus into minus plus 2 into 2, 4. 4 plus 4 is 8. So take the square root. Therefore 1 by square, sorry, 2 by square root of 8 comma minus 2 by square root of 8. Even you can split the square root of 8 into the square 2 into root 2. Okay, so this is the square root of 8. Therefore we can cancel 2. Therefore this is nothing but 1 by root 2 comma minus 1 by root 2. Same thing we will get. Okay, so therefore given any orthogonal set, we convert into orthonormal set by normalizing each vector by its norm. Okay. So now what I am saying here by the theorem, if A is symmetric matrix, then A is orthogonally diagnosable, and A has full set of n orthonormal eigenvectors. So there are, maybe you will get n eigenvalues. For each eigenvalue, you will get an eigenvector. The eigenvectors are form an orthonormal set. So that means what? If you take the inner product of any two different vectors, the inner product is 0. If you take the inner product of same vector, you will get 1. Okay. So this is very important for this symmetric matrix. So symmetric matrices are orthogonally diagnosable, and all the eigenvectors of symmetric matrix are orthonormal. Very important. Okay, so from this you can easily say we are in the yesterday class I said that if a matrix is diagnosable, the algebraic multiplicity equal to the geometric multiplicity. So what is the algebraic multiplicity of a lambda eigenvalue is number of times repeated. So what do you mean by the geometric multiplicity? Is nothing but the dimension of the null space A minus lambda. So in this case both are equal. Okay, so sometimes they call eigenspace. So maybe I can say here, suppose lambda is an eigenvalue of any matrix. Okay, suppose lambda is an eigenvalue, eigenvalue of A. eigenvalue of A, where A is an n by n matrix. Okay. Now, what is the so suppose okay, what is the now we define what is the eigenspace. We usually they usually call E of lambda. So E of lambda is nothing but actually null space of A minus lambda I. So what is the meaning of this? What is the definition of this? We are collecting X, capital X, small x. Okay. We are collecting the solution of this equation A minus lambda I x. So now, so this is nothing but collection of all x in Rn such that A minus lambda I times x equal to 0. The solution of this equation A minus lambda x equal to 0. So sometimes we call it null space, sometimes they called eigenspace. So this space is nothing. This is a space. So this space is called eigenspace of lambda. Eigenspace of lambda. So the dimension of the eigenspace is nothing but geometric multiplicity. So the dimension, because E of lambda is a subspace, therefore we can talk about the dimension. So the E of lambda we define is nothing but geometric multiplicity. Geometric multiplicity of the eigenvalue lambda. Since for symmetric matrix, so suppose we take m of lambda, m lambda. So m suffix lambda is nothing but is arithmetic multiplicity. So arithmetic multiplicity is the number of times the lambda repeated in the roots of the characteristic polynomial. So arithmetic multiplicity of the eigenvalue lambda. So for symmetric matrix, these two numbers are equal. That is the dimension of E of lambda, that is the geometric multiplicity, equal to algebraic multiplicity for the symmetric matrix, because symmetric matrix is diagonal. For diagonal case, the algebraic multiplicity is always geometric multiplicity for any diagonal matrix. If you take symmetric matrix, if you take the unitary matrix, if you take orthogonal matrix also, it is diagonal matrix. Okay, so that is very important. Now, we define what is the normal matrix. So when we say yes, complex matrix is said to be normal if satisfied A into A star equal to A star into A, but it's not equal to identity. It satisfies the commutative property, but that is not equal to identity. In that case, we say it's a normal matrix. So definition: a complex square matrix. A complex square matrix A is called a normal. It's called a normal matrix if A into A star equal to A star into A. That's it. If it is equal to identity, then we call it a unitary matrix. Okay. Sometimes not all the matrix satisfied A into A star into A equal to identity. Okay. If we satisfy this A into A star equal to A, then we say A is normal matrix. Suppose this is equal to identity, then we say that matrix is unitary matrix. Therefore, all the unitary matrices are normal matrix, but normal matrix need not be unitary matrix. So yeah, matrix had to be normal. This is very important. So keep in mind what is A. Sometimes some books they use A theta, some books they use A power h. Okay, so what is the meaning of these? It's nothing but just you take the conjugate of each term of the matrix and then take the transpose. That is now I am using A star. Okay, so these are all same meaning. A star or A theta, A power h. So these are all nothing but just you have to take the conjugate of each term of the matrix and then take the transpose. Okay. Now, therefore, from this definition, we can say every unitary matrix is normal, because unitary matrix means what? A into A star into A equal to identity. Therefore, anyway satisfied A star A star. Therefore, every unitary matrix is normal. but converse need not be true. Converse means every normal matrix need not be unitary matrix. Therefore, the converse need not be true. Sometimes may be true, but in general not true. That's why I am saying need not be true. Okay. Now we have some. Naturally we ask, these normal matrices are diagnosable or not? So that is the next question, next theorem. So when this normal matrix is diagnosable, if it is upper triangular, if the matrix is upper triangular and then normal, then that matrix should be diagnosable. So if theorem, if an upper triangular matrix, if an upper triangular matrix T is normal, then it is diagnosable. Then it must be diagnosable. Must be a diagnosable matrix. In general, normal matrix need not be diagnosable, but if it is upper triangular, then the normal matrix is diagnosable matrix. Now we make some theorem statement, some characterization of normal. Okay. So now theorem. So the theorems are very important to solve the problem. You should remember all the theorems. Okay. So for any complex matrix, for any n by n complex matrix, then the following are equivalent. Then the following are equivalent. So what is the first statement? A is normal. Okay. So maybe we call the matrices A. So we can take here. So a complex matrix A. Okay. Now A is normal. Normal. Then second one is this A is unitarily diagnosable. Because it's complex matrix, therefore already we know that it's diagnosable. Now suppose if A is normal, then A is unitarily diagnosable. Therefore, no need. If it is upper triangular and it is normal, then it is diagnosable. Now, this theorem is more powerful that if it is normal, it is unitarily diagnosable. Therefore, every normal matrix is unitarily diagnosable. Okay, and then third one is A has full set of orthonormal eigenvectors. A has a full set of, that is n by n matrix means there are n eigenvectors are orthonormal vectors. Full set of n orthonormal eigenvectors. Okay, so far what we discussed, what are the diagnosable matrix? All Hermitian matrix, all skew Hermitian, and then unitary matrix. These are all unitarily diagnosable. And then for the real case, so far we discussed only the symmetric matrix is orthogonally diagnosable. And then one more thing here, the complex matrix A is unitarily diagnosable. Okay. Okay. Now orthogonal matrix is also orthogonally diagnosable. Okay. So these are all very important theorem. So using this, we can solve many problems. Okay, now what we have to do? Okay, we already Now one more thing is Jordan canonical form, but it is not in the syllabus. But you should know about this one. Okay, anyway, I think this is not in our syllabus for the exam. So Jordan canonical form. We start with every matrix. We have a row reduced echelon form, row echelon form, right? So we can one more matrix we can produce, that is Jordan canonical form. So we can form that matrix using the minimal polynomial of the matrix. Okay. Anyway, I'm not going to discuss that Jordan canonical form because it is not in the syllabus. Now I come to this. When we say a linear transformation is diagnosable, so far we discussed only for matrix. So yeah, when we say a matrix is diagnosable, it is orthogonally diagnosable, means it is similar to the orthogonally similar to the diagonal matrix. So now, when we say a linear transformation is diagnosable. So anyway, any linear transformation from finite dimensional vector space to finite dimensional vector space can be viewed as a matrix, right? Already we know that. Okay. Now, suppose definition. Suppose let V be the n-dimensional vector space. Let V be an n-dimensional vector space over R. N-dimensional vector space over real R. Over the real R. And suppose let T is a linear transformation from V to V. The linear transformation. Be a linear transformation. Anyway, it's a linear operator. Okay, now because the domain and the codomains are same vector space, right? So let we take linear transformation. It's not issue now. Linear transformation. And we say the operator, the linear transformation T is diagnosable. Okay, so we can say if T is diagnosable, so if there exists a basis, for the domain B and then codomain, anyway both are same. There is we can find that there is a basis. With respect to the basis, we can represent this linear transformation as a matrix, right? Because already we know that every linear transformation from finite dimensional to vector space to finite dimensional vector space, we can represent as a matrix. Using the basis, we can represent the matrix, right? Therefore, when we say a linear transformation T is diagnosable, if there is a basis, maybe we call that basis, we call some name, script B. So we can call the basis script B. Okay. So there exists a basis script B for V such that the matrix, so for V such that the matrix representation of T with respect to this basis is the diagonal matrix. Otherwise, it's a diagnosable matrix. It's otherwise diagnosable or diagonal. Okay. So proving showing A is diagnosable, we have to prove that the corresponding matrix representation is diagnosable. That is, we can find a basis B for V such that the notation. So what is the notation? This is a notation to represent the matrix representation of the linear transformation such that this. What is the meaning of this? Matrix representation of the linear transformation. Matrix representation of T is diagonal. We get the diagonal matrix, then we say T is diagonal. So not for all the bases, for there exists a basis. That we can find a basis such that the matrix representation of T is diagonal, then we say the linear operator is diagnosable matrix, diagnosable linear operator. Okay. Okay. Any doubt? Okay. Okay. Now we solve some problem. So the first problem, suppose we have they given the matrix. So problem number 1 or exercise 1, example 1. Suppose there are 4 real numbers. So A, B, C, D are non-zero real numbers. All are non-zero and real numbers. Real numbers. And with the condition that with what is the relation between this A and B are, so A plus B should be equal to C plus D. This satisfies this condition. These four numbers satisfy this condition. Now what is the question? Then the eigenvalue. Then an eigenvalue of the matrix. Eigenvalue of the matrix is, so what is the matrix? 3 by 3 matrix. A, B, 1, C, D, 1, 1 minus 1, 0. So what is the answer? So the first answer is A plus C. The second option is A plus D. And then the third one is A minus B. The fourth one is B minus D. Now what we know, the sum of the eigenvalues are nothing but trace. The product of the eigenvalues is nothing but determinant. Now we know the relation between A, B, C, D, that is A plus B is nothing but C plus D. Now how to solve this problem? So can anyone? So just you got to find that first you got to find the characteristic polynomial. So that is the only way. So what is the characteristic polynomial? And then you got to find. So that is determinant of A minus lambda I. So solution. So we have to subtract lambda on the diagonal. Therefore A minus lambda, B 1, C, D minus lambda 1, 1 minus 1, 0 minus lambda, that is minus lambda. So what is the determinant of this? So we can expand via the first row. Therefore A minus lambda times minus C lambda. Oh no, not C lambda. Minus lambda times D minus lambda. Minus plus 1. Minus B times minus C lambda minus 1. Plus 1 into minus C minus D plus lambda. Okay. Now simplify this, what will get? A minus lambda times, multiply minus, we get minus D lambda plus lambda square plus 1. Minus, you can take minus outside, therefore plus B times, or multiply B inside, therefore B C lambda plus B minus C minus D plus lambda. Multiply this A minus lambda, so you get minus A D lambda plus A lambda square plus A. Now multiply minus lambda, minus plus D lambda square minus lambda cube minus lambda. Remaining things are BC lambda minus BC minus this plus lambda. Now we can arrange in the decreasing order, minus lambda cube. Then what is then lambda square? If you take lambda square outside, so what will you get? A plus D. Only 2 terms. Now you can take lambda outside. If you take lambda outside, minus AD and then minus 1 plus BC plus 1, right? And then the constant terms are plus A, then plus B minus C minus D. Correct? Yeah. Now you can simplify this. So minus lambda cube plus A plus D times lambda square. You can cancel this 1, therefore plus BC minus AD into lambda. But we know that A Okay, look at this here. So what is this? A plus B equal to C plus D. You can take C plus D to this side. We get A plus B minus C minus D is 0. Therefore, this entry should be 0. The last entry should be 0, right? So therefore, we'll get a quadratic polynomial. So therefore, you can take lambda outside. So if you consider the equation, characteristic equation, what is A minus lambda I equal to 0, implies that you can take multiply minus, therefore we can take lambda outside, we get lambda square minus of A plus D lambda plus, sorry, minus. Otherwise plus, we can write AD minus BC equal to 0. Now therefore 0 is the one of the eigenvalue. Okay. Now we have to solve this. This is a quadratic thing. So what is the roots of this? You can use the formula minus b plus or minus square root of b square minus 4ac by 2a. So if you apply this, so maybe directly I can write. So therefore 0 is the one eigenvalue. Another eigenvalue is a plus d a plus d plus or minus, okay, that is plus b plus c by 2. This is a one eigenvalue. Another eigenvalue is a plus d minus b plus c by 2. Apply this formula, you will get this one. So this is the eigenvalue. Now, what is the what they are asking? What is the eigenvalue? What will get? Use the condition a plus b equal to c plus d. Therefore, this c plus d is nothing but a plus b. Again, a plus b, 2a plus b. Therefore, 2 to cancel, we get a plus b. Okay. Therefore, a plus b is the one of the eigenvalue. You can cancel 0 is the one of the eigenvalue, but in the option 0 is not given, right? But the option given is only the terms. Therefore, a plus, okay, sorry, a plus d or a plus, I think, I think options is, I think, some mistake. I did the second one is a plus b. Now I am writing a plus b. Sorry. So this is a plus b. This is the correct answer. Okay. Now we solve another problem. So usually they will ask what is the eigenvalue and all. Okay. Now please wait. I can find another one. So already we solved so many problems. So if we miss some problem, I will solve that one. So checking set is subspace or not, right? So you got to check 0 is a number of the set or not. You have to check that the addition should be in the set and then scalar multiplication should be in the set. So that is very simple thing. So I leave it to that exercise. Now, any other problem? So almost we solve all the problems, right? Okay, please wait. So in the book I found some problem if you need. So if so far any doubt, you can ask. Yeah, maybe one more problem is there. Now, simple problem. So this type of problem they will ask frequently. So what is the problem? So suppose they will give the eigenvalues, and then they will ask about eigenvalues of some other matrix. Okay. What is the problem? Exercise 2. So simply directly write the problem. Suppose A is a 3 by 3 matrix. Okay, and then the condition that trace of the matrix, it is given that 3. Okay, and the determinant is 2. Determinant of the matrix is 2. And suppose it given that if 1 is an eigenvalue of A, it is given that 1 eigenvalue, because it's a 3 by 3 matrix, it will have 3 eigenvalue. They give the 1 eigenvalue is 1. So 1 is an eigenvalue of A. Then what is the question? Then the eigenvalues of the matrix A square minus 2 times I are. So the first option 1. Okay, anyway, no need to write all the option. Now we solve the problem. Now it is 3 by 3 matrix. So it is given that 1 eigenvalue is 1. And we know that the sum of the eigenvalues, the product of the eigenvalues is given. Suppose we call alpha, beta, gamma are eigenvalues. Because it's 3 by 3 matrix, it has 3 eigenvalues. There are 3 eigenvalues, we call alpha, beta, gamma. So anyway, it is given that 1 eigenvalue is 1. Therefore, better without lot of generality, first we assume that lambda alpha is 1. Therefore, 1 comma alpha, sorry, beta comma gamma are the eigenvalues. Now the sum of the eigenvalues is nothing but trace. What is the sum? 1 plus beta plus gamma is 3. Okay. Now the product 1 into beta into gamma, the product eigenvalue is nothing but determinant. So from this, what is the sum? Beta plus gamma is 2, 3 minus 1 is 2. So beta plus gamma is 2. Beta into gamma is also 2. Right? Now, what is the eigenvalues of this? A square minus 2A. 2I. So better. So we know the eigenvalues of A are 1, beta, gamma. Therefore, what is the eigenvalues of A square? Is nothing but 1 square, beta square, gamma square. So what is the eigenvalues of minus 2I? The eigenvalues of I is 1, 1, 1. Multiply minus, minus, minus 2. So what is the eigenvalues of A square minus 2I? So just sum. 1 plus minus 2 is minus 1. And this one should be beta square minus 2. And should be gamma square minus 2. Okay. Now, tell me what is the eigen. If you know alpha, beta, then we can easily write the eigenvalues of this. Okay.
Sir, 1 plus I and 1 minus I, sir.
Sorry, tell me again. Yeah, 1 plus I, that is beta, and then gamma equal to 1 minus I. Because if you sum these two, I cancel, we get 2. If you product these, A plus IB into A minus IB is nothing but A square plus B square. Therefore, 1 square plus 1 square is 2. Okay, good. Therefore, this is the answer. Now, therefore, the eigenvalues of A are 1, 1 minus I, or 1 plus I, anything, 1 plus I. So, these are all are eigenvalues of A. Now, what is the eigenvalues of now what is you got to find the beta square. So suppose okay, I am taking this beta, okay, anyway. So therefore the eigenvalues of A square minus 2I is minus 1, this square minus 2. What is the square of this? 1 minus I whole square is nothing but A square, that is 1 square, minus 2AB plus B square. B is nothing but I square, okay, sorry, plus I square. I square value is minus 1. Therefore, 1 minus 2I minus 1. So, minus 1 plus 1 cancel, we get a minus 2I. But we have to subtract minus 2. Look at here. Or anyway, we can take this is gamma, this is beta, not issue. So, therefore, minus 2. Therefore, you can take minus 2 outside, 1 plus I. Now, just you square this one, 1 plus I whole square minus 2 value. So, this is nothing but A square plus 2AB plus B square. Again 2 to cancel. sorry, 1 cancel, we get to 2i, therefore 2i minus 2. If you want, if you take 2 outside, we get this one. Okay, so I think answer is minus 2. Yeah, correct. This one is correct. So this is eigenvalue. So first you got to find the eigenvalues of a. So and then you can easily find the eigenvalues of a square minus 2y. Okay. Now we solve one more problem. Third problem. So I'm directly right. Suppose given that there are two numbers n and m, but m not equal to m. Okay. So there are two linear transformation. One linear transformation is T1 is a function from Rn to Rm. So another linear transformation T2 is a function from Rm to Rn. Okay, B linear transformation. B linear transformation. There are two linear transformations. Such that what is the condition? The composition T1 composition T2 is bijective function. It is given that it is bijective. So bijective means what? 1, 1 and 2. Then which of the following is true? Then the first option is rank of T1. R means rank. Okay. So the rank of T1 is n. It is true or false. And the rank of T2 is m. The second option, the rank of T1 is m. And then the rank of T2 is n. The third option, rank of T1 is n, but again the rank of T2 is also n. The last one is both are m. That is rank of T1 is also m, rank of T2 also m. Then which of the following is, which one is correct? So how to solve this problem? So it is given that T1, so composition of two linear transformation is also a linear transformation. Now we can write here. So what the given? So from, okay, I will change some color. So there are two functions. So from Rm to Rn, what is the function? T2. From Rn to from Rn to Rm, the function is T1. Now the composition T1 composition T2 is a function from Rm to Rm. Okay, so it's a function from Rm to Rm, and it is given that is bijective. So bijective in particular is 1, 1. So 1, 1 and 2. And we know that a linear transformation is 1, 1. What is the kernel of this T1 composition T2 contains only singleton 0. So that means what is the nullity of this one? Nullity of T1 composition T2 should be 0. By rank nullity theorem, what is the rank of T1 into T2? Should be the domain. What is the domain dimension? M. Now we know that the rank of T1, T2 is M. And we know that, what we know? Rank of AB is less than or equal to minimum of rank of A comma rank of B. And then is greater than or equal to rank of, so maybe we can, I can write here. So the relation is rank of T1 plus rank of T2. What is the common things I can here? So we can see as a matrix. So what is the matrix? This T1, M cross M, M cross M, and this one is N cross M. Okay, therefore, what is the product? Should be M cross M. Therefore, common is N. So N less than or equal to rank of the product T1 into T2, and this should be less than or equal to minimum of rank of T1 comma rank of T2. We know this anyway. Now what is, so it is given that composition is bijection. So you should know some basic real analysis. Suppose composition of two functions is bijective, then one of the functions should be 1, 1. So what is that? Maybe you should, if you know the real analysis, that is very simple. So maybe I quickly recall here. Suppose F composition G is 1, 1. Okay, then I think F is not F, G is 1, 1. We will check now. So proving we know that F composition G is 1, 1. I think G is 1, 1. So how to prove G is 1, 1? So I will check here. Suppose I am taking G of X equal to G of Y, and what we have to prove? X equal to Y. Now apply F both the side. Therefore F of F composition G of X equal to F composition of G of Y. This is nothing but again F of G of X. But F composition G is 1, 1. Therefore X should be equal to Y. Therefore, if the composition of two functions is 1, 1, the first function should be 1, 1. Clear? Now it is in our problem, it is given that T1 composition T2 is bijective. Now we take 1, 1 case. Because both 1, 1 and 2, better take 1, 1. So therefore implies that what we know, the first function T2 is 1, 1. If T2 is 1, 1, implies that what is the null space of T2? Single and 0, therefore the dimensionality should be 0. By rank nullity theorem of T2, what is the domain of T2 is M. Therefore rank of T2 should be M. Therefore rank of T2 should be M. Okay. Now again the same thing. Suppose the composition of two functions is onto the second function is onto. That is, suppose F composition G is onto, implies that the first function F is onto. So how to prove this one? That is very simple. Okay, so maybe I draw the picture here. Okay. So what is the picture? Suppose this is some set, and this is another set, and this is another set. Okay, here we have function, and here there is some function. Suppose I am call this function is F, and this function is G. Okay. Now total function is from here to here. We call that function is F composition G. Okay. Now what we have to prove? This function is given that onto. Now we have to prove this F is onto. So that means what? If we give any element here, we can find a pre-image to here. Okay, got it? So that is our aim. So how to find? Suppose you give some element. I take some Z. Suppose we call some name. Okay, so this is a X set. This is a Y set. Maybe take this Z set. Okay, that is G is a function of X to Y. F is a function of Y to Z. Now we are going to show that F is onto. Therefore, if we take any element Z, small z in capital Z, what we have to put? We have to find small y here, such that F of, we have to find, that is our aim, find y in Y such that, and F of Y should be Z. We have to find such a Y, that is our aim. Okay, keep in mind. Now, what we know, this function F composition G is onto. Therefore, if we take any element here, we can find a element here. Maybe we call that element is X. Suppose since we know that F composition G is onto, if we give any element here, we can find the element X such that this X maps to this Z. That is, since F composition G is onto, implies there exists a X in X such that this F of, or not F composition G of X should be Z. But we need this F of Y. We have to find Y. And we know that given any X in X, but we have a function G from X to Y. Therefore, this X maps to somewhere here. We call that element is Y. And this Y actually going to map this. So, So since G is a function from X to Y, therefore this X maps to some element. We call that element Y. Therefore, what is this Y? Since G is a function from X to Y, we know this, and X is an element in X. Therefore, this G takes the small x to some element in capital Y, we call small y. Okay. Now, substitute x. Therefore, the composition
Sir, voice is breaking, sir.
am I audible now? Okay, so now, so if the composition is onto the first function is first function or second function, okay, depending upon your choice, but the first one it should be onto, right? Now, in our case, T1 composition T2 is given that is bijection. So bijection means what? In particular, it is onto. Therefore, here I can write here the T1 composition T2 is onto. So since this onto implies that the first function T1 is onto. So T1 is onto, but T1 is a function from where to where? T1 is a function from Rn to Rm. Therefore, this onto means what? It should be range space. Range space should be Rm. Therefore, the rank of T1 should be M. The rank of T1 should be M. Because this T1 of the domain should be the entire space, codomain. What is the dimension of this? M. Therefore, both rank of T1 and T2 should be M. So that is the answer. What is the last one? Here we know we don't use this formula, but we can you should know this one. Whenever the composition is 1 1 from the right hand side, the first function is 1 1. If the composition onto from the left hand side, the first function is onto. So once you know it's 1 1, the nullity is 0. If it is onto, the rank is full rank. So okay, that is a important thing. So any doubt in this? Okay, so we can stop now. Thank you.